Right. Good morning, guys. In the last session, we learned the basics of radiation. What exactly is radiation? How it differs from conduction and convection. We learn to know how radiation happens. That means taking an example of a solar radiation, the light from the sun is converted to the radiation form. How actually it is done, and different spectrums of wavelengths for radiation. We are done with the electromagnetic radiation, different spectrums. That means the ranges with which those depend upon the wavelength, because the radiation mostly depend upon the wavelength and the frequency. For that, we also define an equation which is C is equal to lambda f, where C is velocity of light, which is 3 into 10 power 8 meters per second. Lambda is our wavelength, and f is the frequency of the waves, which are basically electromagnetic waves. Today, we are going to see the next topic, or the surface emittant properties. That means we said there is light. If we are taking about a solar energy, the light coming and which is uh, incidented on some surface. Now this surface will absorb either. There are three things, right? Now this can absorb, partly absorb the radiation, or it can reflect the radiation, or it can transmit the radiation. We discussed three things. So for any surface, these three will be the basic things. Either it can partly absorb, or it can reflect, or it can transmit through. So the rate of emission, if it is emitting from this, that means we discussed that on this surface we'll have some photons arranged when the radiation is impinged here. Here, the electrons or anything will excited, and they will be emitted in the form of photons, and these photons will propagate in the form of a wave with with the velocity equal to the light, and reaches the surface with the receiving surface, and there this wave motion is converted to thermal form. That's what we discussed. So first this plate should be emitted. Now we should know the emission properties, surface emission properties clearly. On what factors usually this surface emission depends on? It depends upon the temperature of the surface. What is the temperature of surface? Usually, because as we are talking about the thermal radiation and the heat transfer, what temperature will be the key one? The nature of the surface. It is the physical property of the surface nature. The wavelength, the most important one is the wavelength or frequency of radiation. In the last class, we defined our spectrum of electromagnetic radiation. Different wavelengths or frequency will have different radiations. Take an example of an X-rays, gamma rays, UV rays. Visible, we have visible light region, we have thermal radiation. So wavelength also is a key point for radiation here. So temperature is the basic one, the nature of surface is second one, and the wavelength is also third. So with these factors, following factors, we have some parameters on which we should rely on while defining the radiation part. The first one is total emissive power, which is very important one, denoted by capital E. Total is the complete part. The emissive power is defined as total amount of radiation emitted by a body for a unit area and time. That means if you're taking this as a body, there is some radiation impinged on it. Now, what is emissive power is the total amount of radiation emitted by this body for a unit area in unit time. That means how much amount of radiation is emitted by this body in unit area in unit time is defined as total emissive power. The units for them are watt per meter square. And the emissive power of a black body, according to Stephen Boltzmann, is proportional to absolute temperature of fourth power. This first class or heat transfer we discussed the radiation governing law is Stephen Boltzmann law. There we defined that the amount of heat transfer is always proportional to fourth power of the temperature difference. The same thing, but here we are explaining in the terms of emissive power. That means, according to Stephen Boltzmann law, for a black body, this emissive power is always proportional to fourth power of the absolute pressure. If you see, EB is the emissive power or total emissive power, B represents the black body. That means this total emissive power of a black body is always proportional to the absolute temperature for fourth power. That means T power 4. to remove this proportionality, we have a constant that is sigma, which is Stephen Boltzmann constant, which is where value is 5.67 into 10 power minus 8. That is your total emissive power. Next one is monochromatic emissive power. We define that these emission properties or the emission also depends upon on the wavelength or frequency of radiation. So it is necessary for us to determine the spectral distribution of radiation on surface. That means the wavelength ranges should be defined. That means if on a body there is some radiation impinging, we should define the wavelength of the radiation or the ranges of wavelength. That means it might be from here to here. Usually we define that as in an order of wavelength. That means we cannot particularly say that this is the wavelength. We'll tell that from this range to this range, from 10 power minus 2 to 10 power minus 4. So that is an order of wavelength that we should definitely determine. So it is often necessary to determine the spectral distribution of energy radiation. At any given temperature, the amount of radiation emitted per wavelength varies at different wavelengths. So at a particular temperature, the emitted radiation per wavelength varies at different wavelengths. I will tell an example. Now, for a temperature of 60 degrees centigrade, at a temperature of 60 degrees centigrade, some x value of wavelength is a wavelength of light is impinged here. Now this emission rate will be different too if you are maintaining the same temperature 60 degrees centigrade. But if the light impinging have different wavelengths, the emitting will have different. Getting? You are maintaining the temperature constant, but if you have different wavelengths impinging, will have different wavelengths emitting. So that is what it is. At any given temperature, the amount of radiation emitted per wavelength varies at different wavelengths. For this purpose, the monochromatic emissive power of surface is used. Mono is always 1. So it is defined as the rate of energy radiated per unit area of surface per unit wavelength. So it is an energy radiated per unit area of surface per unit wavelength. If you see, total emissive power is it is a total amount of radiation emitted per body per unit area per time, and but this is energy radiated per unit area of surface per unit wavelength. Here we are defining in respect to the wavelength because different wavelengths will have different emission rates. So for a particularly per unit wavelength, if you are defining the emissive power or the emit energy radiated, that is monochromatic emissive power denoted by E lambda. Okay. Here is our relation for that. E is equal to here because you are integrating the total value 0 to infinity E lambda d lambda watt per meter square is our relation because we are defining that for one each wavelength or unit wavelength. So for your total thing, you integrate it with the total. Next one, emission from a real surface emissivity. What is this? It is actually very simple thing. It is an emission power from a real surfaces. That means we have real surfaces and ideal surfaces. Ideal surfaces are something if we show in the books or in any theories that they'll have 100% efficiency like that. But real surfaces are surfaces which are very practical in nature. Those are real surfaces. So this is the real surface. The emissive power of a real surface is given by E is equal to, you see, it is emissivity. Sigma is our Stephen Boltzmann constant. A is our area. T power 4 is our temperature, absolute temperature difference of 4. This is our emission power or emissive power of a real surface. Okay. Usually we go for E is equal to the formula which we have written there is sigma power T power 4. Right. We shown the emissive power. But if you take area into consideration, we also write area. But here another part which you are considering is emissivity. This is what defines that it is a real surface. Okay. Usually we can write that E is equal to sigma A T power 4. But we are also adding our emissivity E value, which defines that it has a real surface. What is emissivity? It is defined as an ability of a surface of a body to radiate heat. It also defined as ratio of emissive power of any body to emissive power of a black body of equal temperature. This is very important. It is the ratio of emissive power of any body to emissive power of a black body at equal temperatures. That means you take two bodies. One is a black body, one is a simple other body. You maintain these two at same temperatures and see the emissive rate or the emission power. Now, ratio of these two will give us the emissivity of a body. For a black body, it is 1. For a white body, it is 0. And for gray bodies, they are in between 0 and 1. Okay. For black body, it is 1. And for gray body, they are between 0 to 1. And for white body, it is 0. I think we are clear. Now, we'll see later this intensity of radiation and related to density and pressure. Now, radiosity, which is denoted by J, it refers to the all radiant energy leaving the surface. Light impinging on the surface, the energy which is leaving the surface is referred to radiosity, which is denoted by J. So these are some parameters which we should learn. Once again, I'm repeating them to you. The first one is the total emissive power, which is the emission rate or the total amount of radiation emitted per unit area per time. Whereas this monochromatic emissive power is related to the emissive power or the rate of energy radiated per unit surface area and unit wavelength. There is difference between those two. This is our real surface emission power, in which you should define the emissivity, which is the ratio of emissive power of normal body to black body at equal temperatures. This radiosity is refers to the all radiant energy leaving the surface. So these are some of the parameters which we are defining. Now, as I said, on any surface can undergo three things. Can be partially absorbed, it can be reflected, or it can be transmitted. If you see this, here we have an incident radiation G, which is coming on a surface or a material. Here you can see this radiation can be reflected, which is denoted by G suffix R, which can be absorbed, which is G suffix A, which can be transmitted through it, which is G suffix T. These are the three conditions which can happen. So we have an incident ray Gi or G, which can be reflected, which is Gr, which can be absorbed, which is Ga, which can be transmitted, which is Gt. And we should know that by conservation, energy conversion principle, that total energy will always be constant, come what might. So the total energy incidented will be equal to the sum of all these three things, which is reflected, which is absorbed, which is transmitted. If you divide with this G, this is dA by G, that means absorbed by incident. This is Gr by G, which is reflected by incident, which is Gt by T, which is transmitted by incident, which is G by G. Now defining this as alpha, this is V rho, this is tau, is equal to 1. Now this alpha is now defined as absorbivity, which is related to absorption. This rho is defined as reflectivity, which is referred to reflection. This tau is defined as transmittivity, which is related to transmission. That means if you want absorbivity, it is a ratio of the energy which is absorbed to the energy which is incidented. If we want reflectivity, it is a ratio of energy which we reflected to energy which we are incidented. Transmissivity is it is a ratio of energy which is transmitted to energy which is incident. Right? I think you are clear with those things. Alpha is absorbivity, which I said you. Alpha is absorbivity. Rho is our reflectivity. T is our transmittivity. Okay. Now, when the incident radiation is absorbed, if there is absorbed, it is converted to internal energy. Please remember this. We'll see for a black body. For a perfectly black body, the any black body actually happens is the absorbability here is equal to 1 because it absorbs completely. That is the reason why we said that on a hot weather or when a sunny day, we don't wear black clothes because it will absorb the complete energy or the incidented energy. That means that's why your alpha is 1, whereas our rho and tau is equal to 0. If our absorbability is 1 and rho and tau 0, such body is defined as a black body. Okay. For an opaque body, opaque, that means when you cannot go through the opaque body. That means if energy transmitted energy incident cannot be transmitted through it. That means this tau will be zero. So for a opaque body, our tau will be equal to zero. So the equation which we shown before is alpha plus rho is equal to 1 because tau became 0. So we seen black body and opaque body. Now if you go to white body, in white body, if you see all incident radiations falling on the body are reflected. That means our rho will be 1. Our absorptivity and transmittivity will be 0. Okay, for black body, absorptivity is 1. For opaque body, transmittivity is 0. And for white body, the reflectivity is 1. Okay, please remember those differences. Okay, now here white body, we are telling the total thing is reflected. All the energy here is reflected. But here reflection is of two types. The first one is specular reflection. The other one is diffuse reflection. Specular reflection means the angle at which it is incidented will be exactly reflected. That means it is incidented at an angle of theta. It will be reflected at an angle of theta. That is what specular reflection is, or regular reflection. Diffuse reflection is it will be diffused into different radiations. It cannot be only one way. It is diffused into different radiations. See here, this is incident with an angle theta. It is diffused into 1, 2, 3, 4, and 5. That is what diffuse reflection is. So two types of reflections we are seeing. Next one is gray body. Here, what is gray body is if the radiative parameters alpha, rho, tau of a body are assumed to be uniform over entire wavelength spectrum, such body is defined as a gray body. That means your alpha, rho, tau should be constant over entire wavelength of spectrum. That is gray body, which is not changing. It is not 0 once it is not 1, it should be constant. It can also be defined as a gray body is also defined as one whose absorptivity of surface does not vary with temperature and wavelength. Absorptivity should not vary with temperature and wavelength. Means or alpha, which is absorption, for a black body, which is 1, should here for a gray body, it should not vary with temperature and wavelength. That is defined as a gray body. Right. So we are done defining our black body, opaque body, white body, and gray body. So in the next session, we'll see concepts of black body and laws defining these radiation. Thank you.